way. Bosworth, who is one of the architects of the CLR team, I'm not sure, responsible for all sorts of design decisions and tricks inside the runtime that it's really some great low-level hackery in implementation of Speculative dispatch. And he's come up with some even more novel ideas for dispatch. We'll be talking about those.
Well, in a sense, I wouldn't claim these are novel. They're just reapplication of some old ideas in our world. Sometimes there's novelty in that. What I'm going to do is I'm going to start off and give some observations and biases that I have. I think it's useful to give people a context so they can understand immediately why they should ignore what I'm talking about, rather than having to try and glean it from the talk itself. I'm going to talk about the current approach we use for dynamic dispatch. And the particular area I'm concerned with here is virtual functions and interface functions. It's essentially when the code generator wasn't able to determine the actual target address that needs to be called. So I'm not looking at sort of the dispatch style kind of much more dynamic thing here. I'm going to propose an alternative built around stubs and heuristics. I've actually built an implementation of this, and on my machine it kind of sort of works even. So I took some performance measurements of it, and I'll talk about those, and I'll have some observations. In general, delayed binding to me is a good thing. Loose coupling, resiliency, reuse, the list can go on. So anytime somebody asks me to pin something down, I usually say, now's not the time. It's a good answer. V-tables are a bad thing in the large, from my point of view. For those of you who don't know, I have a long background in small talk, so V-tables are something that shouldn't have been invented in the first place. They're space inefficient in the large, and they make a tight binding at the time you generate the code. You have to know the index in the V-table, and it better really be there. And to me, that violates the first principle. It's not a delayed binding. Heuristics are a good idea. They can mask a lot of ignorance, and they can provide for the unexpected. They often allow for things to be used in context that you had no concept of at the time you actually wrote it. And so systems that can kind of glide to the right place don't require you to be smart to understand what the right place is. So hence the approach I took. Our current approach for this kind of stuff is built around method tables or V-tables. The method table, if you think of it, we have an object. It has an associated method table. If you think back in sort of the object sense, we'd call that, it's sort of like the class of the object, although really we have it kind of fragmented out a little bit more. But what the object really points to is the method table. In that thing is the V-table with the virtual functions. In that thing as well is essentially little kind of sub-V-tables for the interfaces that this object supports, so we can dispatch through those. There's an interface table on the side that allows us to map for a given type or object type where its interface tables are for the interfaces it supports. It's sort of the basic notion. We'll get a little more detailed in here. And for those of you who aren't completely sick of this topic yet, here's a little code fragment that defines a few interfaces and a few classes. And on the right is sort of the V-table slot assignments that would come out of this. Now, this isn't necessarily precisely what the V1 thing does, because as you can see, order is somewhat independent here, but logically the number of slots is pretty accurate here. And as you can see what's going on with Class A, since the class method and the interface method share the same implementation, there's only one V-table. The first V-table slot points to that implementation, and then the other sort of method that the class has, which isn't part of any interface for Class A, follows that. And so sort of the sub-interface table is overlaid over the virtual function part, so it's for space efficiency reasons. If we look at Class B, we've now brought in another interface and implemented the method that it needs. And conveniently, we can just add a slot at the end, and nicely the two interfaces line up very nicely, and so everything's nice and compact. And then we come along with class C, and we suddenly decide, gosh, I didn't like that implementation of just the interface method. So I want to change what the interface method does, but I don't want to change what the class does. And that's sort of that little I.2 fragment in front of it is sort of a made-up syntax of mine. C# is similar, but the idea is there. The CLR allows me to do that. And now all of a sudden, we find that we no longer can share that second slot, and we have to move where the interface implementation is to get this little subtable down below. I should point out, in the extreme, if I now made a class D that wanted to change certain other implementations, you can actually end up leaving holes in this method table and sort of abandoning regions that says, well, here's this unused area. There's actually nothing in it. And so it can grow. So there are some potential size issues associated with vtables and so forth. The actual calling sequences for a virtual call is what you'd expect. You load out of this pointer, which is in our calling sequences in ECX, the method table, and then you do an indirected call through it. Because at the time you JITted, you knew the index. And that's what that 4 is. Somebody at JIT time had said, well, where is this method? He said, well, it's offset 4 in the vtable. So away you go. The interface call uses a double indirection scheme here to locate where that fragment is. So basically what's going on was you get the method table again in the same way. In the method table, I didn't show it, but there's a slot at a fixed location that says, oh, your interface map is here. So that's what that XXX is. It bounces through the method table and goes over to its interface map. For those who have access to the code, I should warn you, the term interface map is used for various things. They're not all the same, but we don't need to get into that here, but just as a warning. And now that we have this map, we can then use the interface ID, which is an index. Every interface, when we load the code, gets assigned a number starting at 0, and it's increment and it's global for what's reachable to your program. For those specifically, it's global to the app domain, but anyway, it's a small number, so we can use it as an index. That's what YYY is. Go find where this thing is, and that gives me the address of where the little vtable stub is that the interface is implemented by. Typically, that's in the method table of the class. If you want to get into vagaries like how COM, interop, and a bunch of weird stuff works, it actually could point off to some weird places in corner cases, but we'll ignore all that for now. In essence, it ends up taking you into the method table and says, here's where the little interface dispatch table or interface vtable is. And then, since the method we're calling is the first method of the interface, we have this call EAX plus 0. Obviously, the instruction doesn't have 0 on it. But anyway, we go through the first slot. So in essence, you can see virtual calls, normal indirected call kind of approach. Interface calls does a couple of more indirections, but is basically an indirected call approach as well. What is this interface map? Well, you can think of it as a two-dimensional array, but it's been that would be way too sparse. It would be enormous if it was done that way. So it's tightly compacted. Each class points to its row. The interface ID is how far down to go. And then these things are packed into a very tight structure. How that packing works really isn't the subject of this talk. It just basically works, and it grows. We have a lot of statistics that show that it grows pretty linearly with the number of interfaces that you have. So what I did is I took a look at a bunch of little programs and took some statistics on what's in the method table. How big is it? What are the different pieces of it's used? Warning, this was done several months ago. We changed the code a lot, so if you ran this, you'd get different numbers, but the idea and the relative sizes aren't that far off. So if you look at a program like Hello World, which does what you'd expect, in the particular build I did, it was 269 method tables or types in that thing that were loaded. Now, actually, if you kind of get the current build, whatever, I think it's down to like 63 or 61 or some number like that. But the point is, there's a bunch of them. What's the total size? That's the next column of them. How many of those are slots? How many bytes are tied up in slots of various kinds? That's what we got there. And then you have sort of like static data and GC information and sort of a kind of interface mapping information that's unrelated to that other interface map I talked about. So this is sort of a breakdown of the space. You can see in some cases it adds up to a fair amount of space. That VS Forms miners were getting up close to a half megabyte in his method table kind of space. And there's a fair amount of slots in use as well, spread across those things. So anyway, here's a kind of a slice through a hierarchy. This is kind of give a question of, do these things start growing rapidly? What with all these interfaces coming in and so forth. So here we come down from object and kind of look at it. Kind of an interesting column. Really here as you look at the one is VT, which is the number of bytes tied up in VTable. In the VTable for that type, you can see it's just not too big. And they see this big whack jump at control. And then it doesn't grow much very more. Is something weird going on in control? Well, no, in the sense that nothing unusual is happening other than it has a whole lot of methods and a whole lot of interfaces and a whole lot of stuff. Now, you can argue whether that's a good implementation or not, but from the point of view of how the method table grows with respect to the amount of methods you actually write, things are behaving normally. And you can see, just to give you an idea, if you look over the interface map, from that I can ascertain that control is implementing, I don't know, 15 or 17 interfaces are introduced at the level of control in the hierarchy. So there's an awful lot of little subtables in that method table. But after we kind of get the base one, as we extend it along, it doesn't dramatically grow anymore. So then you can sort of ask the question, how many of these VTables do we actually use, and how many of the slots do we actually use? And so this sort of says, if you look at threshold is kind of lets me take slices about kind of frequency. So it's sort of like saying if it's used, the threshold 1, if the usage is at least once or more, and 2 at least twice or more, and so we kind of have a varying level of how heavily things are used. What's the number of actual VTables defined in the program? You can see this was a different run that was run quite a bit later, and we had managed to reduce the number of method tables that Hello World used significantly. So instead of 269, it's 164 now. Of that, we used 8. 8 had one slot used at least once in a VTable. And how many slots were tied up total in the 164 tables? Well, it was 2,000, almost 2,100 slots. How many slots actually had any call at all to go through them? 26. If I looked at VTables that were actually used, what was the total size of those? And that's what the next column is, 269. And how many virtual calls are there in this program? 46. What it sort of tells you, it's a tiny little program. So it's kind of interesting to look at a bigger program. This is VS WinForms Designer, which is sort of a variant of WinDes, which is sort of a design layout tool. This is an interesting program because it actually does a GUI and it does a whole bunch of stuff and uses the WinForm hierarchy, and I can give lots of good reasons for it. For those in the product groups, you would know that the real reason why I picked this is it's in the BBT tree. Somebody else makes sure it works all the time, so when I want to run a test, I can just pick it up and run it. And I don't have to keep trying to port this thing to each release. But it is a nice sized program. You can see this thing's got like 2,000 types are actually loaded into the system when it runs. And of that, we use less than 500 are used at all during the run. And those 2,000 slots, 2,000 types take almost 60,000 slots to hold, which is 240,000 bytes. So a lot of space in slots. How many slots do we actually use? Well, less than 4,000 are actually used at all. And if I could just figure out which VTables were actually being used, instead of 60,000, I have 20-some thousand of these things. And this particular program trace is making over 2 million virtual calls. I'm not counting the direct function calls and whatever. It can be a lot of those. These are just the virtual and interface calls. And if you kind of look at the threshold number, this sort of gets to the question, well, how often are they really used? And if you start walking down this thing and saying, well, what if I limit my focus to things that are only used, a half dozen or a dozen times or so? You can see the number of types in use, which is the used column, the first one, starts dropping pretty fast. The number of slots starts dropping pretty fast. that you actually go through, the number of virtual calls that you pick up doesn't drop very fast. So it says most of the actions happen through very few. And in fact, if you follow this thing down to the bottom, you can find, well, sort of the interesting notion is when I got to the bottom, there's like 12 or a dozen or so slots that have over half of all the calls going through them, which sounds a little weird. We'll come back to that in a minute. But so the observations are, really, there are not a lot of types being instantiated. Of the 2,021 are possible, just a fraction are used, and most of them not very much. If we start looking at the number of sort of tuples, type, member number, the number of tuples is not that big. And you don't have to even get very many to pick up a large fraction of the program. And that something weird is going on in WinForms. 4 particular slots are using a whole lot of calls, and they happen to be in a hash table. And that's so, we kind of threw this over the fence at the WinForms guy. This is data that's many months old, and said, look at this, maybe you can improve WinForms. And in the product group, you throw it over the fence, you assume they do the right thing. So I'm assuming they've done something, and I haven't tried to track all that down. Yes?
Why is I presume hash table doesn't have multiple implementations in the system. Why are they making virtual calls at all, given that there's only one implementation?
Well, you can have more than one implementation of it. And because it is marked as virtual, the compiler can't and the JIT can't solve the solution. In hash table, you're allowed to provide your own hash function. So there's some things that are there as part of the extensibility framework for a hash table. And, we can go into a long discussion of why hash table is the way it is and whether it should be changed or so forth. And that's not actually the topic. I might agree with some of those comments. Yes?
I think the biggest answer to that is the fact that hash table is the primary implementation of either iDictionary or iCollection, which is used quite extensively.
What turns out one of the big uses here is walking and managing properties and how that's done. And it was in the WinForm designer area, but whether it's done well or poorly or whatever, as I say, that's something I threw over the fence.
George, you haven't given any indication of the destinations. How many of the virtual calls actually end up going to different destinations? I mean, how many of them have you?
Yes.
Will you give information?
Yeah. And so here's some other programs that maybe aren't weird in the way that the WinForm thing was. The first one is sort of a DOM-oriented thing, and the second one is sort of a DB-oriented thing. The thing to notice here is that you get the same kind of pattern. They don't have the anomaly at the bottom, but I mean, basically, not a lot of types actually get instantiated. Not a lot of slots actually get used. A few slots, it doesn't take too many, and you get a huge number of the virtual slots covered, whatever. So, the observation, again, about vtables is they do require the code generator, or the JIT, or whatever is generating your code, to bind to a slot number. So you can't decide later. And things like dynamic invocation for scripting might like to decide later, so it actually uses a different mechanism than vtable dispatch, which is horribly slow. And other languages might like to do something different as well. I come from a Smalltalk background, so there's some issues in trying to get things to work efficiently for Smalltalk. Other binding approaches like multi-methods. In other words, I want to make the decision based not just on the type of the this pointer, but on something else, or something more, or something less, isn't possible. And you can't detect out of range in a vtable. I mean, you could. At every call site, you could do a range test, but that would make vtable dispatch horribly slow. And so you've got this version resiliency extensibility problem that most people kind of sweep under the rug. We've got this kind of Faustian bargain between the guy who writes the code generator, which generates these offsets, and your versioning mechanism and the underlying loader. And if they don't get it all right, your program will vector off to God knows where, and you'll never know. And you've got this thing, you pay for them whether you need them or not. vtables have to be fully populated, fully allocated, whether you're going to use them or not. So that sort of is my motivation for why I was thinking about what's an alternative. So what's really going on here? What do vtables actually do? They essentially provide a mapping function from a calling frame and a ref token to a method implementation address. And vtables are a restricted form of this. The only thing, the calling frame of interest to vtables is the this pointer, or the type of the this pointer in particular. And what is the ref token? Well, I'm calling it this contract member pair. If you, I love the word contract, so I often overuse it. But the basic notion is, if I look at a type, if it implements an interface, I'm calling that a contract. And the actual sort of virtual functions that it implements, not through an interface, I'm calling another contract. And so any mapping function that did this would be a perfect replacement for vtables. In fact, you could implement it as a mapping function, except you'd suffer from slowness. So what are asymmetries I can leverage? How is what's going on skewed? And what are the important skewness to take advantage of? Implementation of runtimes is all about lying and cheating. Find out why the world isn't uniform and take advantage of it. And don't do what you really say you're doing, but make sure people can't catch you at it. We're going to try and use very heavily the notion that few types are actually instantiated and a small number of slots are actually used. We're going to make an assumption. This is not out of the blue, because past history has shown us that this is true from all sorts of studies of languages in the past. Most call sites are mostly monomorphic. That you can kind of infer from the previous charts when they said I had a few slots that were making up most of the calls. And if you start looking at the number of methods, number of target addresses you hit, you don't hit many target addresses. But we'll do some measurements to try and verify that after we do it. So a simple alternative is sort of to say that at the call site, I'm going to call some stub of code which will do the right thing. And we'll explore what do the right thing is. And then eventually we'll end up at a target method address. And what we're going to do is we're going to make these stubs specific to the type that's actually coming through at the call site and the method or the token or this contract member pair that call site is trying to reach. We're going to recognize that there are at least two different kinds of stubs we've got to worry about, mostly monomorphic, and we hope that's what's going on most of the time. And then there's going to be those where that's not true, and we better make an allowance for it. So we want something that works very well when things aren't mostly polymorphic. We're going to assume that we can build these stubs on demand. So we don't want this, pay all up front kind of approach. And we're going to try and say that there's some sort of heuristic that we're going to use to choose and adjust what kind of stub is in use. So you can think of this as code rewriting logically. Whether we actually do code rewriting is another issue. So let's kind of formalize this model a little bit. Call site is call stub address. For those a little more interested, I could make that an indirected call and make it pure code, but for the discussion of the logical model, that's not different. Initial stub address is going to take me to something that just pushes the token and then jumps into the EE somewhere and says, go figure this out. And the end result of that is that the call site's going to now point somewhere else. And we hope what it usually points to is something like this, which is the monomorphic style. It says when we come through, we're going to see whether the type of the this pointer is what we expect. And if it is, we've burned into the stub what the target address is. And we're just going to go to it. And if it's not, we're going to run off to the EE again and say, hey, that didn't work. Fix it up. Find out where we're really supposed to go. And so what I did is I modified the FJIT, which came up earlier. What is the FJIT? It's just a easy to modify JIT, which isn't terribly efficient, but it's easy to whack. And that's why I whacked it. And I had to generate a trace of all of the virtual calls actually being made as they're being made, along with some other statistics. And then I took those traces and fed them through a program I wrote, which simulated this model and tried to take statistics from it, like how many call sites that we're seeing, when are we making stubs, when are we hitting, when are we missing on this simple assumption of the mostly polymorphic kind of stuff, and so forth, how many types are showing up and so forth. So unfortunately, these start getting a little harder to read. Here's a program which is OLADB test, and you see the virtual call number going down here sort of. I have it, at the very time we hit the very first virtual call in the system, we actually build two call sites in that method by this point. We've got one stub because we actually called something. It missed because it wasn't there when we called. We've JITted 82 methods by this point, which shows that there are a lot of methods that don't have virtual interface calls, is all that's saying. And we had to load 18 classes so far. And what you're seeing in each line is deltas as you go down. So you can see mostly you don't miss that often, and you slowly start jitting in the code. And this is obviously at the very front end of the startup. So if you move farther down the trace of this program, and now again, this is at virtual call 1,000 and then down to virtual call 2,000, you can start seeing, well, what's interesting about this table mostly is they're mostly zeros up there. And when they're not zero, they're small numbers. And the miss column is small. Okay, so things are mostly monomorphic in this program. And we don't have huge numbers of stubs being made either. So we're not seeing new tuples coming at us that we hadn't, which is getting at the question of how often is the target address different? How many different implementations are we going through? Every time we go to a different implementation, it would require us to build a new stub. So it's in the gross level, it isn't happening that often. So this looks very promising. I actually ran a whole bunch of programs through this thing, and they all pretty much say the same thing. Here's sort of the summary statistics for that program. There are 3,000 call sites that we actually JITted. We only actually called through 2/3 of them. This one has 850,000 virtual calls in it, and of that, 2.8% using this very simple model would have missed. So this kind of mostly monomorphic does really, really good. And across all the programs, it's a small number like that. It can vary around by a few percent, but it never gets big, is the point. We don't make a lot of stubs. We only had to make 897 stubs. We only had 121 tokens. That's sort of this contract member pairs. There are very few of them that actually show up. Why is that? Well, if you think of what contract member pair is, it's essentially vtable offset. And so you can't have more of them than the longest vtable you got. And you're certainly going to have less than that because you don't go use every slot. So that's why that number is small. I can inject entirely new types unrelated in the hierarchy, but their slots numbers still start at 0. And away they go. As you can see, most call sites have very few stubs appear at them, which says how many target addresses are we actually going to out of a call site. The answer is mostly 1. It either isn't called or it goes one place. And how often, the other thing is kind of saying how many call sites end up going to the same place. And the answer is, well, about 6. Method 6. Now that's averaging in even the ones that weren't called, by the way. But anyway, so 5.5. So all that just means is you've got several call sites in the program that are calling the same thing, and they're seeing the same actual type coming through. None of these are surprising numbers if you've looked on past statistics on other languages and other environments of the last 20 years or so. If we look at the program statically, it's got almost 1,000 types in it, well over 10,000 methods, and well over 20,000 slots in it. So there's a lot of space. When I said you had to buy it all up front, you would have had to buy a lot of space. Yes?
How long does it take to actually fill in one of these stubs? I mean, it looks like it would be pretty quick, but it's hard to calibrate the 2.8% unless
I actually built an implementation, and we'll show numbers. But that comes later. Whoops. Question is monomorphic, polymorphic, or how do the kind of misses? I've got this sliced and diced a lot of ways, but this is one of the interesting ones. It says let's look at the miss rate of call sites. So that's why this is sort of got. If you're wondering why 9 isn't there, this printout admits lines that are all zeros. There was one line that was all zeros. But anyway, what's the miss rate? How many calls actually were involved at that call site that exhibited that miss rate? How many sites was that involved? You can see that the 0 one is very promising. We've got a lot of calls going through sites. Through most of the sites, they effectively never miss. And that's where most of the stubs are, too, which is most of the stubs get used exactly once. Or going to the same place. So anyway, It's promising. You get down here, obviously, when you're looking at things that have higher hiss rates, miss rates, you're seeing more misses. But what's nice to notice is that this number is small relative to that top number. Okay, which says that, yeah, you got to worry about polymorphic stuff, but that isn't going to be what's going on mostly in your program. So you don't need to worry about it really hard. So I built an implementation of this thing. Whacked the CLR, whacked the JIT. This time it wasn't the F-JIT, it was the normal JIT. So I could do full retail builds and all that kind of stuff. And the CLR, or the EE, generates the stubs, maintains caches of them, it implements those things like if I have to look it up, what's the stub, and if things are polymorphic, and the heuristics of when to switch back and forth, that's what it does. The JIT generates something different at the call sites. I'll show you that in a minute. What wasn't done in this implementation? I didn't bother to eliminate the vtables themselves. They're not being used, but I didn't eliminate them. This wasn't an attempt to be a product implementation. This was a proof of concept, so I didn't need to do that, get the measurements I wanted. I didn't integrate all the stub mechanism with app domain unloading. In the full solution, you want to be able to deal with the issue of unloading an app domain, and then a lot of these stubs need to unload with it, so you need to sort of make your stubs and your stub storage relative to the app domains. But the actual implementation is set up so that that's easily added. The atomic update of call sites, when I say it's partially undone, to be more specific, I also implemented this in the F-JIT in which it was fully done. And in the normal JIT, there's like two approaches for getting the atomic update. One is adding a level of indirection. That's fully done in the normal JIT if you want these calls to be indirected so that you can have a place to and produce pure code and have a place where you update the stuff. That all works just fine. If you want to have rewriting the calls site directly, typically you've got two choices. You can align so that you can have a place that you can atomically update. And getting the JIT to align my code was more work than I cared to bite off at this point, so I ignored that. And if you're willing to limit yourself to like Pentiums, you can actually atomically update something that isn't aligned with using weird instruction sequences that are slow, but what the heck. You don't do it very often. So I didn't bother to do that because it's all provably feasible, and for what I am trying to do, feasibility is the point. So what were my tokens? Well, actually, the tokens were two 32-bit fields, the contract and the member. Notice those are mostly small numbers. So it actually doesn't store structs most of the time. It bit encodes them in the right in line in a 32-bit pointer. It's actually got a way of, it will handle big tokens. It's just they never happen. So what does the call site look like? Well, it just isn't that different. We load the type, which is sort of what all the other things did, and then we just call the stub. Okay. And that's marginally smaller than the existing call site because, or marginally bigger, depending on how you call that stub. But anyway, it's not much change in the actual call site size. Now, if you're trying to do it with pure code, you would call indirect. So that's what happens at the call site. When you first JIT the code, what's it going to actually land on? Well, it's going to land on one of these things that says, we don't know what we're doing yet, push the token, and go into the EE and fix everything up. And so we're placing the bet. When we go into the EE, we're going to build something that says, that's sort of saying that this type is what we expect, and we'll figure out where it goes, and we'll burn that in. Or in other words, we'll make the monomorphic bet the first time we hit this thing. So what does that entail? What are we actually going to build? We're going to build something that looks like this, which says, remember I loaded the type in EAX at the call site, so is it what I expect? If not, go off somewhere and fix it. Otherwise, go to the method. If you're familiar with sort of branch characteristics, you'll understand why you want that to be a forward jump, but we'll revisit that later. So the fail stub needs to cause a lookup to be done, and then pass control the correct method. Notice that we build one of these per the tuple, expected method table token, which if we go back to those original slides was that number that said how many tuples I'm seeing, and it was in the hundreds, so even for fairly large programs. So it's not going to blow up on it. It doesn't appear to be blowing up on us. In theory it could, but it doesn't look like real programs actually do. What's the fail stub do? Well, the fail stub starts getting concerned about, is this thing really a polymorphic or monomorphic site? One note is that there are a lot of dispatch stubs that may point to this fail stub. The dispatch stubs can share it because you're only going to generate one of these per token. So every dispatch stub that was built for the same token can point to the same fail stub. So you start getting this great reduction in the number of stubs you actually need. And what it basically does is it decrements a counter and says, is this happening a lot? And if it is, we're going to jump off to some patch stub that says, let's think about switching the world around a little bit because this isn't working so well. Otherwise, it falls into something that says, let's do the polymorphic thing. Okay. Patch stub does what you'd expect. Just goes in the E and says, fix it up. And if it decides it will, it'll turn it to a polymorphic site, which was pointed to the same place that we fell through to. And this looks like a lot of code, but basically it's a hash lookup. Check for a hash hit. If it is, go to the address. If not, go back in the EE and say, find out where it really is. So there's really no magic going on in these stubs. They're pretty straightforward. Key point here is that your cache hit rate is going to affect your performance quite a bit. So I didn't spend a lot of time on that because I figured that could be done in a real implementation. So here's a best case scenario. What if I just write a bunch of inline calls in a loop that are all completely monomorphic? What happens? We got the loop costs for a bunch of counts. The current gen D stubs is if I force it to always call the dispatch stub. And the R stub is what if I always force it to do the long inline cache lookup thing? And what's the perf difference? The call in static are the current implementations. I had to whack the E so it didn't inline because it would have inlined all this shit. So this is after I turned the inlining off. And then we have the interface, and the virtual is using the stub mechanism right now. And, whoa, it's not too bad. We're slightly faster in interfaces. The interface dispatch is slightly slower in the virtuals, which is if you think about the code sequences that you mostly go through, that's not surprising. What's the worst case kind of program? Something that's really polymorphic. So Richards was lying around, got a kind of a straight port to C#, and then I whacked it so everything was a virtual call. And I mean everything. You want to read a piece of state, you did a virtual call. And then I whacked everything to be interfaces. And here are the statistics here. It slows down a lot. But it's not too bad. The most disturbing characteristic is what the heck is the difference between these two numbers? If you look at what's above, they're about the same, which is the code paths aren't markedly different, yet the time is a factor of 2 different. What the heck's going on? Spent a lot of time tracing it down. And lo and behold, everything is completely unstable. Small changes in something that have absolutely nothing to do with this can make those things jump by a factor of 2. Spent days with vTune. Built post-processors to the vTune raw counts. All sorts of shit. And then I spent hours reading the Intel manuals. And that led me to build hard-coded sequences that absolutely controlled everything. Where I could vary the calling site and the environment in which the call was done. And basically had a loop of 20,000 around 50 inline call sites with no ops to vary alignment between them and different other maybe putting instructions in there, maybe not. The thing I'm calling either being a bare return or building a frame. And so here are the numbers. And generally don't look too bad, but that table, if you look at it closely, still full of anomalies. Okay, that you can't quite explain. They're not terrible. So then, after reading the manuals closer, I said, what happens if I vary the code size? So here we have small is a loop of 20,000 around 50, large is 1,000 over 1,000. Both 1,000,000 calls. Loop overhead should be negligible. Everything should time the same. It doesn't. It varies up to a factor of 4. Okay? And in particular, virtual calls go to hell. They just get whacked. The stub stuff doesn't get hurt so bad if it's direct stub calls, and the indirect doesn't. And the reason for that is the branch transfer buffer. And if you bring vTune on this thing, you can prove that. Those are just statistics on my machine, by the way. What I had Pentium 3. And the reason why that kills you is this is how branch prediction is done on the Pentium in very rough terms. You've got, what if I can guess it right away? And that involves the BTB. What if I can statically figure out what's going on? Like it's a direct call or a direct jump here. That only costs you a half dozen cycles. And what if you didn't get it right? It's an indirected call. I have no idea where it's going, or it was a jump conditional and I guessed wrong. It's a score or 2 score cycles, and that has nothing to do with caching, memory bandwidth, cache lines, whatever. That's just the processor got messed up and it's got to clean up its pipelines. How big is the BTB? It's tiny, relatively speaking. I think that's the Pentium 4 number. I forget what the Pentium 3 is. It's either the same or smaller. It's also very complicated. I won't go into the complications of it. But that led me to do this. Let's go back to my simple call. Again, this is just a loop in C#, doing calls, static calls, interfaces, virtuals. Here we had what we had before. Here we reduced the loop count and increased the amount of inlining. And lo and behold, you see, even in not hand-built code, but the actual generated code of our system shows the same kind of anomaly in it, where you can get killed by the BTB if you're doing a lot of branching. So, the conclusion is stubs can be performant. Perf is hard to measure. Things like the BTB can make that almost impossible to figure out what's going on. And something people who generate code sequences got to keep in the back of the mind. Transfers of control of any kind, branches, calls, returns, anything, put pressure on the BTB and can therefore have a hidden perf cost as your program scales up in size. So. Gosh, that's do all the sleep. Yes.
You talked about throwing stuff over the fence, not knowing what they did with it, but you sort of have this periscope looking in their backyard where if you rerun your tool against it, you would see if they, did something about it. So,
Well, they did rewrite. I don't have statistics on it that I've run off, but yeah, they did rebuild some of the stuff and make some design changes in what they're doing. There was a limit as to how much they could do in V1 and so forth, but it certainly was something they looked at very hard. And then there's also trying to understand the actual usage that WinForms is making the hash table. Some of it's very legitimate. Some of it is around sort of pre-caching stuff that often doesn't get used, so they can kind of tune that. So
short of whacking the JIT, if we wanted to improve the situation in our code, is there something not obvious that we might do to cut down on the amount of space being used by detailers?
Something not obvious that you could do. Well, the more methods you define, the more VTable slots you're going to take up. That's basically what's going on. And if you suddenly walk up with a class that wants to implement, 15 or 20 or 30 interfaces, it's got to build all these extra subtables on it. So do you really need, what does it mean to have a type that implements 30 interfaces? I don't know if that's logically a well-thought and designed type. So some of it, I think, just comes at normal design issues.
Take one more question.
Does did the pure code implementation suffer dramatically more as a result of the BTB?
The pure code implementation ran at about the same speed in the large as the vtable stuff, precisely because it had indirected call in it.
No, but I mean as opposed to where you actually wire in the new call site.
Yeah, that's what I mean.
Obviously, I guess that would so
it looks about the same as our current virtual call mechanism there in the large, because it has an indirected call.
Basically always missing in that situation.
Well, now the problem is you're missing because the BTB can't find it. I mean, it's statically going to the same place. It's always going to the same place, but the chip can't figure that out, is what's happening to you.
So even if you use this method, if you still rely on pure code, you see little performance.
Pure code comes at a cost, is what I'm saying. The indirections cost you a lot, whether you're using virtuals or whatever you're using. Anytime you're saying I'm going to introduce another call side, just a direct call puts pressure on the BTB, and an indirect call side means when the pressure gets hit, that's where it's going to show up.
That's actually where half an hour behind time.
Okay.
Every workshop I go, all schedule always goes. Luckily we've got lots of padding this time, so I think we're going to have lunch at 1. So we've got 3 quick talks to follow up now.
Lunch at 12:30, right?
Is it lunch? Is it? Well, we will have lunch at 12:30 now. Yeah, we was going to be 12. We'll be 12:30 now. For half an hour. We'll restart on time at 1. But first we'll have 3 short talks. First, I've actually cancelled mine. We need to cut the time out of the schedule. So actually, I haven't had the chance. I'll give the talk properly another time. Once I've got these sorted out better. And first, Nick, followed by Chris. And followed by back with George.
Okay, so this is literally a 5-minute talk. I'm not sure I can plug that on to something. Yeah, 5 minutes plus microphone arrangement. Okay, so this is not a talk about any actual research I've done or anything. It was just a question that I asked myself whilst I was doing some unrelated work. And the basic question is there any point in having continuations in the runtime or a similar runtime? So for those of you who don't know what a continuation is, the basic idea is it's the idea of making first class the idea of the rest of the computation. So the context in which you're doing something can be turned into a heap allocated object, which can then be passed around, and you can then return to a previous context. Or, rather interestingly, one of the most powerful things you can do with a continuation is simply not use it at all. So to a first approximation, if you think in implementation terms, then it's something like grabbing your current stack and turning that into an object on a heap, and then there's a way of making that be the current stack again. So the thing is, this single mechanism allows you to build all sorts of groovy control structures. So you can build exceptions on top of this, you can build Prolag style backtracking, you can build coroutines, you can build lightweight threads with some kind of preemption and user-defined scheduling, you can build stateless servers. It's quite a useful abstraction for building migratory computations. Various things to do with security can be expressed in these terms. You can do time travel debugging, where you grab the current state of the computation periodically, and then in the debugger you reach something interesting, and then you can go backwards in time by returning to the state of the computation previously. And the thing that I've been playing around with is, in fact, it turns out that continuations are a universal computational effect. So if you think evaluating some expression, if you're an expression-oriented language, returns a value and does some other stuff on the side, it turns out that continuations can express once you've got continuations, you can change what the notion of side effect that your language has, all within one. Just based on continuations. So this is so lots of people have seen, I guess, the sort of using continuations to do threads and so forth. So this is something a bit different. This is this arbitrary computational effect. So what I'm going to do here, this is a piece of standard ML that runs in a version of standard ML with first-class continuations. And what I'm going to do here is I'm going to take already compiled code. And standard ML is not a language which is non-deterministic normally. What I can do is I can take already compiled code and I can magically make the language behave as if everything was non-deterministic, simply because I've got call CC in the language. So by doing a bit of call CC magic, I can define these 3 functions. And the clever part here is there's a function called pick, which takes a list of things of type alpha and gives you back an alpha. And there's a thing called fail, which gives you back a thing of type alpha. And results is just some gubbins to run around the outside. So here's an expression which says let x be non-deterministically 1 or 2, let y be non-deterministically 2 or 5, and then I'll evaluate the expression that says if x equals y, then I'll fail, otherwise I'll add x to y. And if I run that in this little results wrapper, I get back indeed the sums of non-deterministic choice of those two, non-deterministic choice of those two, but cutting out the case where I pick 2 and 2. But the neat part about this, you see, is that this stuff is all operating over lists of integers, but this addition operator here is the built-in addition operator that's in the language that doesn't know anything about the fact that it's going to be called in a non-deterministic way. So here's another rather entertaining use of continuations. So client sends a request to the server. Server starts executing some code in response to that. Oh, this seems to be the wrong version of PowerPoint. My animations aren't working. Ugh.
Yes.
I spent hours on the plane doing this. This is the only thing I've put any time into in this talk was messing around with animation, and we're not going to see it. So I'm not quite sure what's going to happen. Anyway, so the server starts running some code, and at some point, when the arrow's got down to here, it's got some result. Oh, pitiful. Oh, I'll have to do it by hand. Right, so request comes across, server starts running some code, and now normally the server sends some kind of response back to the client, and if this is some kind of stateful computation, the server records somewhere where it's got to in the computation, and then when this client comes back with a response to the response, it'll pull back from the storage where it got to in that computation for that session and carry on. But the idea of stateless servers is that the server runs some script on this side and then sends back to the client the continuation of the computation it was performing and the result. They both move over here. Now the server can forget all about the transaction it was engaged in with that particular client, because all the state information about where it got to in the computation is shifted across to the client. Then when the client resubmits the next response, it comes back with the continuation, then the server can pick up the continuation that it's fed back and carry on. So this way, all the work of keeping track of the state of all the possible interactions with different clients is decoupled from the server. So, history of the idea of continuations. It's quite a nice, they're a nice thing. They were invented in semantics of programming languages rather than in programming languages first, in order to give an explanation for what simple jumps actually do. But then they fed back and they've become a popular programming language construct in languages like Scheme and SML of New Jersey, and there's lots of people still working on them, even though the basic idea is fairly well understood. There's uniform translation of your favorite programming language into what's called continuation passing style, in which every function gets an extra argument, which is what to do with the result of this computation. And when you do that, every call becomes a tail call. So question, why should you have first-class continuations in a VM? Well, so we have this continuation passing transformation, which will take a language with continuations and turn it into one, compile it to one which doesn't have. But if you want to compile a language which has first-class continuations, like Scheme, then if you do the CPS transform and then stick that onto the runtime, performance is absolutely spectacularly terrible. And that's doubly true on our runtime, where our tail calls don't really work properly, in that they're slow and they don't get taken when you've got security on. Similarly, there are lots of other languages which has features like backtracking, or where the programming model requires you to be able to produce thousands and thousands of very lightweight threads. And all those things are hard to implement. And this is one mechanism that would enable you to do all those things. So I think a general purpose runtime should provide general purpose mechanisms rather than hardwiring lots of things in response to demands. On the other hand, they're actually quite scary. I mean, it's one of the most head-spinning areas of programming language theory. And as soon as you think you understand it, then you just suddenly start looking at what happens when you CPS transform programs which are in CPS style and so forth. So there's lots of complexity associated with thinking about this. It almost certainly interacts badly with lots of existing features, security being an obvious one, and probably rules out some optimizations, which might mean that even languages like C# which don't use continuations might pay an efficiency cost. So I don't really have a conclusion, but but since I've been playing with continuations and decided they were quite a cool thing, I just wondered whether anybody had thought seriously about having support for first-class continuations in our runtime or possibly in others. That's it. George.
The answer to that question is yes.
Oh, good. Right.
That doesn't mean we figured out how to do it.
Do you have conclusions?
No. His observations are correct. They're bad interactions, and it's a hard problem. And boy, you research guys ought to work it out.
I know, yeah, it was just a question which occurred to me whilst I was doing something else with them. But yeah, okay. Security in particular seems a bit dubious, but there are lots of other optimizations that people do that aren't valid in the presence of first-class continuations. So I could try on that.
Have you thought about using the fiber mechanism to do linear typed continuations?
So that's a sort of built-in heritage type mechanism.
The fiber mechanism in NT.
I haven't experimented at all. I said I just wondered whether adding this made sense. But, what does that let you do?
Basically, take the switch stats.
Right.
It doesn't package up the stack into a reusable object, but it lets you switch to, basically grab it, say, okay, I need a stack now, and I'm going to hold on to this one,
right, and
later I'll come back to it.
Yeah. So I mean, the extra power for doing all these more exotic things, you do require these things to be first-class objects. But yeah, I'm sure there are some languages which could benefit from using that for simple lightweight trades.
Yeah, did I understand correctly that all of the state that's preserved is what's on the stack?
Yeah, so the call CC is like the whole stack. In fact, you probably don't want to stick call CC in as your basic primitive. You can use call CC to build other control operators, but what you really want is some kind of delimited thing where at some point you can say, this is the point where I want to start paying attention, and then you just grab some part of it. Yeah. Okay.
It's the internal one. Yeah. I'm sorry. That's fine. I got it on this machine. Cool. Here it is. Try this. Oh, okay. Hey, this one. Here we go. Next one's this one. I gotta cancel that. So this is about adapting a fairly common mechanism from data compression for use in virtual machine instruction set designs. It allows you to interpret directly a compressed code. So a quick review of the data compression method. This is a variation on LZ77, which is what's used in most of the zip utilities in CAD and so on. The view from 30,000 feet is the way these things work. Is they take an uncompressed stream and replace redundant material with what you can think of as a back pointer. This -5/8 says go back 5 bytes and make a copy at this point of 8 bytes that you see there. So we're going to back up 1, 2, 3, 4, 5. We can't copy that capital B because it's different from the little b that's redundant, that begins the redundant sequence. And at this point, we're going to copy 8 bytes. Well, right now there's only 5. 1, 2, 3, 4, 5. But by the time we've copied them, there'll be 8 bytes total there. Okay? And then finally, we return to a literal mode to copy the period. With me? Now, typically, this is encoded in a form that I've taken some poetic license with the with the, 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 of bits that tell you whether you've got literal bytes uncompressed or one of these back pointers. What this is saying, it's as though there's a byte in the compressed sequence that says we have 1, 2, 3, 4, 5, 6 literal bytes for the BLAH space B. Then we have one of these back pointers, and then we have another literal byte. With me? And then these tell us how to interpret the rest of the bytes. So we have 6 literal bytes, BLAH space B. Then we have one of these back pointers, which I'm assuming here is a 2-byte sequence, half a byte that says how much you're copying, and 1.5 bytes that says, sorry, I've got this backwards. There'll be 2 fields here, one that says how much you're copying and one saying how far back you have to go to find it. Okay? Should have had 8005 here. And then finally we return to literal mode to catch the period. This is how these things usually work, is something like this. But in a VM environment, we could think of these bits here as instructions. Okay? One that says we have a literal byte, and another that says go back 5 positions and copy 8 bytes. Okay? Well, now we're set up. You could imagine adapting an existing VM. Here I've used the MSIL as a sample, where you've got some stream of instructions. You could imagine adding another instruction, call it echo, that says go back 30 places and copy 3 instructions. Okay? If you were interpreting, we've all implemented VMs before, you could imagine how you would do this with a little stack of how many echoes I'm nested down inside. And there's a lot of detail we don't have time for right now, where you could imagine echoes wanting to use part of a previous echo instruction. You have to be sober to get these details right, but it can be done. If it helps, you could think of this sort of as sharp include, but interpreted on the fly rather than blowing things up. Originally, I called this the sharp include instruction. Another way to think of it is it's sort of like a call instruction or a JSR instruction in a real machine. But it differs in that the caller delimits the extent, the beginning and end of the code that's being reused. And that has the nice feature. You probably wouldn't want to make a routine out of something that did just 3 instructions. The entry-exit sequence would swamp any of the compression value you would get. But if you can grab a freebie from the stream, something that's already there, then it can pay off. And that's really what's going on here, is we're avoiding the entry-exit sequence so we can just steal something out of the stream that we've already paid for. Okay? So I've actually implemented this on a different VM, on a byte-coded representation of the internal form for the retargetable C compiler LCC, which is easier for me to change than any other C compiler because I wrote part of it. And I'm getting about 40% compression. This bytecode is not initially compressed really in any way. It isn't bloated particularly either. It's just sort of a naive, straightforward bytecode. It's a lot like the base instruction set in MSIL, except the operators are typed, which is helpful in an interpreted environment. So, in summary, this thing suits interpreters. It probably doesn't suit JITs because a JIT is decompressing anyhow. The one exception to that is if you're in a JIT environment where you're JITting a bunch of stuff and throwing it away. That is, you're confining yourself to a small buffer, and what's really around all the time is the VM code. Then you could imagine this being of some use. I'm thinking, like a CE device or a phone. In fact, when you talk to people at conferences, the people who show maybe the most interest in something like this are people who are implementing what's called feature code in cell phones. This is stuff that it doesn't matter how slow it runs. They're happy to interpret. What they can't afford is any more ROM. Okay. So that's the presentation. I do a couple of other things too in the same general venue. If this is sort of partly what you're interested in, but not quite, I've got some other gizmos for generating compressed byte codes, compressed XML, and also do some work on table-driven code generators and jitters. So, the end. Any questions? We got time for questions? Gideon.
The semantics of echo are, I think, precisely those of one of the flavors of the perform verb in COBOL.
You'll have to give me a citation for that. I'd like to.
On McCracken. You better read McCracken. You keep your sanity.
Okay. Others? Yeah.
Encryption. How does this interact with encryption on where you're downloading these things?
Gee, I haven't thought too much of that. I mean, it is normal, I think, for encryption packages. I'm not an expert on this, to compress first, just to reduce the redundancy, because redundancy is a way to attack encryption. On the other hand, you'd probably want. This does have some constraints on it. You can't really jump into the middle of an echo instruction, so I have to give up the ghost at beginning and end of basic blocks. Whereas a batch, decompression tool would not have that constraint. It would compress better and probably serve an encryption package better. That's about all that I can think of to say about that. I don't know enough about encryption to say more. Okay.
I failed to introduce either of the last two speakers, I think. That was Nick Benton, that's from Microsoft Research in Cambridge, and Chris Fraser from Microsoft Research here in Redmond. George, you already know.
Yeah, so I'm going to just mention, I didn't make slides on this because it's perhaps too speculative to be worth putting on paper, but I want to get a reaction to. Right now, the CLR has the notion of an app domain, which is an isolation region, kind of like a very lightweight process. And one of the constraints that app domains have is you can't get a pointer from one app domain into another app domain, so that either a code pointer or a data pointer can't be gotten. So they're truly isolated. In the vein of trying to make things highly dynamic, can you take advantage of that? Right now, we can load and unload app domains. What would it mean to stop an app domain? The idea is, what would it mean to stop an app domain and reorganize it while it's running? Now, I can certainly think of times when one can think about doing that, where it's not too hard. For instance, if I could say that there was no stack frame on any thread that was active in the app domain, then since there can't be pointers in the app domain, that means there's nobody. There are absolutely no pointers into this app domain. There's only things going on in the app domain itself. So at that point, I certainly could do something very extreme. I could decide to reorganize the shape of objects, because those types exist only in the app domain, and the instances only exist in the app domain. I could rebuild the code completely differently if I wanted to, because nobody's referencing the code. It's not active. I don't have to rebuild stack frames or try and win. All the hard problems are gone. That situation does arise occasionally, so certainly, and one could maybe loosen the constraint a little, and much like for a GC, we say there's safe points when we can run the GC. We don't just run the GC arbitrarily. I could say that there's app domain safe points, which says that, yeah, there is this code frame, but the code manager for that knows how to reorganize it, if we can invent what the reorganization rules are. So that's okay. Go ahead, and when it gets time to reorganize this thing, we'll kind of rebuild the frame on the stack, because the code manager knows how to do that now. That may be hard to do and be very restricted what can happen. I'm just mentioning it's probably possible. So then the question is, why would one want to do all this stuff? Well, the observation is, much like I did with the stub stuff, is most data is read and not written. Going further, most data is never written at all, The only thing you ever read are default values. And so we allocate all the space and all the objects or all the slots for the state uselessly. If I could rebuild app domains, and since we have this control of who can do it, I could generate the code initially for an app domain to say none of the state lives in the allocated object, that there's some state buffer somewhere that will allocate space in on demand. If you actually write, we'll make a space for it and assign a location then. And of course, getting to it will be slow. It'll go through some long code path to do it, but you don't do it very often. And if you read data and you're just going to read the default value, well, all the objects of a type can share that, so we get massive sharing on that until you actually write it. Things will run slow, but you can consider a program running like that for a while and then saying, oh, maybe we kind of understand what this thing really does now, or at least it's had a chance to heuristically do something. We'll stop it. We'll say, find a point when you can stop. And when you stop, we'll rebuild all the objects and move the state into the object that was actually needed and rebuild the code to now access that state quickly. And you can do this again and again and again. If you also start looking at that, that's one use of this kind of mechanism. Another use of this kind of mechanism is consider the resiliency you get from ASP.NET, because it essentially says your request comes in and we have this thing that is going to process the request. And if something goes weird, it constantly hits a point where we can just shoot it in the head and say, well, we'll kill that app domain and we'll bring a new one up, or maybe we'll kill the whole process and bring another one up, and the user of this is all irrelevant to again. Everything works seamlessly. Well, you're sort of getting that same notion of I have a point in time when I can tear down app domains and rebuild them again just because things weren't the way I expected, or I placed bad bets, or something strange happened, and potentially get a way of getting more kind of adaptability and resiliency into the system. So anyway, that's the basic notion. There's a lot of hard questions in how to implement it and so forth, but that's just another tangent that I think people could explore, because there are the basic starting building blocks for doing that in the CLR, and obviously a lot of work to try and flesh it out and make it actually work. So, questions? Yes.
Rather than doing it at runtime, have you thought about doing, like, the OSs have a lot of their built-in optimizers that users immediately turn off, but eventually they run and try and optimize their hard disk and optimize everything else. We thought about just encoding information, extra information either in the metadata or someplace else, so that later on when the user optimizes their hard disk, they get better performance for the next time they run.
Well, you can do that. I mean, the problem there is, yes, you can do that. You can say I can have a system that uses this scheme of kind of putting everything on the side, and your program runs slow every time you run it. And eventually the system says, well, this has been run a bunch, and we'll kind of offline in the background, we'll have kind of been consuming this data, and we'll figure out some strategy, and then we'll build it. Now, that assumes that you actually turn the program off and turn it back on repeatedly. And if you're doing that, that's an okay strategy. And the extreme of that is sort of like in a web farm scenario. And I've mentioned this to people before. It's a very similar idea. Since I got all these replicated versions of something, I can set one of them up as a profiling one, feed 2% of the workload in, or some very small percentage, so that it can run slow, but it doesn't have much to do, so the response time to users is not noticeable. Gathering statistics, and assume if I'm sending a kind of a sampled stream into it, it's getting a characteristic view of what's going on, and it can sit there and grunge and whatever and figure out a new optimized approach. And then it actually image the thing out, and then you can kind of replicate it back through the farm, precisely because in ASP.NET you can shoot processes in the head and bring them up without interrupting service. So you can roll this thing back across the farm. So that's perfectly doable, and in the farm scenarios is an excellent way to go, and I think people need to start looking at that. My question was, can I move the same notion into a world where I don't have that repeating, the program stops and it restarts, or I have lots of copies of it. Typically on my workstation, I got one thing, and I tend to run things for a long time. So can I then get it back? And this was sort of, how can I get that characteristic back? Questions? Yes?
Well, would this also be a framework for doing things like the work that was done with Dynamo? Could you also work that sort of code rewriting?
Well, you could. Yes. Yes, and it opens all sorts of speculative optimizations. In other words, once you have this kind of characteristic, you can say, well, I think I know what's going to happen, so I'll generate very specific code sequences that say I know the types I'm going to get, and I'm going to get all sorts of bits about what's happening, and I'll just generate the code, and I won't even generate the what if it's not this. I'll just generate it, say, go off, and we guessed wrong, rebuild it, guys, kind of thing, and make sure that those kinds of places where I vector off and say I didn't do it happen at points where I can rebuild the app domain. So it does open a whole new range of dynamic optimizations. And in fact, you can do extreme things at that point. Like you can say sort of speculative pruning of the type tree. I have a virtual slot. I happen to notice that there's no other implementations other than this one. The heck with it. We're just going to call it directly, and we'll hook the app domain loader and say if another class shows up that's a subclass, we guessed wrong, we got to throw the code away and rebuild, but it's probably never going to happen. Most things that can be subclassed never get subclassed. Yes?
These are all pretty much just JIT and EE optimizations, right? There's nothing in emitted code that you could do, and since we don't really have opt-IL anymore, there's really no...
Well, the nice thing about these things is you don't have to change the IL at all to do any of this stuff.
Right. But neither can the compilers give you hints about what would make more sense to do.
Well, okay, where it's going to show up is, yes, you may have to make some provision to be able to pass some information from the compiler if you're trying to define this notion of when is a safe point to unload. That may not be something you can solve completely, so you may need to get more points where you can unload this app domain, some way of the compiler or somebody stating, you know, we're prepared to handle a request to rebuild a stack frame, and I know how to do it. So that may require kind of an extension. The interesting point is that even if you didn't have that in the IL stream, there probably are other points where there's just never anybody in the app domain at all, and you can still do it. So it's sort of like what you do is you can sort of make it work, and it would have a backward compatibility story to existing stuff, and maybe it would be slightly more responsive with newer compilers. So it kind of fits in a nice way, let's say.
Okay, let's so we have half an hour for lunch, and we'll start at 1 o'clock.